After nearly 5 decades of exploring the uncharted vastness of space, NASA's Voyager 1 spacecraft, the most distant human-made object in the universe, has sent what could very well be its final message back to Earth. As it drifts farther away from the solar system, its transmission has captivated scientists and space enthusiasts alike. With each passing year, Voyager 1 continues to send back valuable data, offering unprecedented insights into the mysteries of deep space. But as the spacecraft grows increasingly distant, what do its last transmissions mean for the future of space exploration? The Voyager mission began in the 1970s, driven by a rare and timely alignment of the outer planets. Jupiter, Saturn, Uranus, and Neptune were positioned in such a way that one spacecraft could visit all of them in sequence using gravity assists, maneuvering through space and gaining speed by utilizing the gravitational pull of the planets. This alignment, which occurs only once every 175 years, presented an exceptional opportunity for NASA to explore the far reaches of our solar system. In light of this, NASA launched the Mariner Jupiter-Saturn 1977 program, which was later renamed Voyager. The mission involved 2 spacecraft, Voyager 1 and Voyager 2. These probes were designed with the potential to visit not only Jupiter and Saturn but also the more distant planets Uranus and Neptune, provided they survived the harsh conditions along the way. The spacecraft were launched in 1977 from Cape Canaveral, Florida, just a few weeks apart. Although Voyager 2 was the first to launch on August 20, 1977, the numbering of the probes referred to their order of arrival at Jupiter, not the launch dates. Originally designed for a mission that would last only 4 years, the Voyager probes far exceeded expectations. Both spacecraft are still operational more than 45 years later, making them 2 of the longest-running space missions in history. What was initially thought to be a brief journey to explore the outer planets has transformed into an ongoing odyssey into interstellar space, providing data that has revolutionized our understanding of the solar system and beyond. One of the key factors behind the mission's success was the clever use of gravity assists. By flying close to a planet like Jupiter or Saturn, the spacecraft could steal some of the planet's orbital momentum, gaining speed without the need for additional fuel. This technique, known as a gravitational slingshot, was essential for reaching the outer planets. The outer planets are spread far across the solar system, and no conventional rocket could carry enough fuel to visit all of them. Gravity assists allowed the Voyagers to continue their journey with less fuel, reducing travel time and power requirements. In the 1970s, the technology behind the Voyager spacecraft was groundbreaking. Each probe was equipped with just 69.6 kilobytes of memory, far less than a single modern smartphone photo. Despite these limitations, NASA engineers devised ingenious ways to store, compress, and transmit data across vast distances. The spacecraft did not store information on modern chips but used ruggedized 8-track style magnetic tape recorders, similar to old cassette systems. These recorders were designed to withstand the extreme conditions of space, including radiation and temperature fluctuations. Communication with Earth posed another challenge. The probes transmitted data at an incredibly slow rate of just 160 bits per second. NASA's Deep Space Network, DSN, with its massive 70-meter dishes located in California, Australia, and Spain, enabled continuous communication despite Earth's rotation. Each probe was powered by 3 radioisotope thermoelectric generators, RTGs, which converted heat from decaying plutonium into electricity. The Voyager probes achieved their first major milestone in 1979 when they arrived at Jupiter. This gas giant, more massive than all the other planets combined, has a massive magnetosphere, swirling clouds. The Voyager probes achieved their first major milestone in 1979 when they arrived at Jupiter. This gas giant, more massive than all the other planets combined, has a massive magnetosphere, swirling clouds, and a host of moons. The spacecraft captured images and measurements that far surpassed anything that could be observed from Earth-based telescopes at the time. Among the most exciting discoveries was the detection of volcanic activity on Io, one of Jupiter's moons. Voyager's data also revealed the mysteries of Europa, another of Jupiter's moons, with its smooth, cracked ice surface. This observation sparked a revolution in our thinking about the potential for life in the outer solar system, suggesting that a liquid water ocean might lie beneath the moon's icy crust. Later missions, including the Galileo orbiter and the upcoming Europa Clipper mission, owe much of their direction to the revelations of the Voyager probes. After Jupiter, both spacecraft continued on their journey. Voyager 1 reached Saturn in 1980, followed by Voyager 2 in 1981. Saturn's iconic rings, long a subject of fascination, turned out to be far more complex than anyone imagined. Instead of broad concentric bands, the rings were composed of thousands of narrow ringlets, each with its own dynamic features like spokes, braids, and scalloped edges. These features arose from interactions with Saturn's moons and the planet's magnetic field. Voyager 1 also made a historic flyby of Titan, Saturn's largest moon, revealing the secrets of its thick, nitrogen-rich atmosphere. Although the data gathered was invaluable, the flyby altered Voyager 1's trajectory, preventing it from continuing its journey to Uranus and Neptune. While Voyager 1 was diverted by Titan, Voyager 2 continued its path and made history by becoming the only spacecraft to visit Uranus and Neptune. In January 1986, Voyager 2 flew by Uranus, revealing a planet unlike any other. Uranus was found to be an icy giant with a strange tilt, about 98 degrees, causing the planet to roll sideways as it orbited the Sun. This unique orientation, believed to be the result of a massive collision in the distant past, added to the mystery of this distant world. Voyager 2 also discovered Uranus's faint rings and new moons, some of which exhibited strange surface features like fractures and canyons, raising new questions about their geological history. The spacecraft also uncovered the peculiarities of Uranus's magnetic field, which is tilted and offset from the planet's center. These discoveries remain a cornerstone of planetary science, and scientists continue to analyze the data gathered by Voyager 2, decades after the flyby. The mission culminated in Voyager 2's arrival at Neptune in 1989. Neptune's atmosphere was found to be filled with the fastest winds in the solar system, and its great dark spot, a storm similar to Jupiter's Great Red Spot, captivated scientists. However, Neptune's storms are more transient, appearing and disappearing in short time frames. Perhaps the most surprising discovery, however, came from Neptune's largest moon, Triton, which was found to have active cryovolcanoes venting nitrogen gas. This unexpected finding raised intriguing questions about Triton's origins, especially given its retrograde orbit, suggesting that it might be a captured object from the distant Kuiper belt. After completing their exploration of the giant planets, the Voyagers began their journey into new territory, interstellar space. Both probes pushed farther and farther into the unknown, studying the solar wind, cosmic rays, and the boundary between the solar system and the interstellar medium. In August 2012, Voyager 1 crossed into interstellar space, becoming the first human-made object to do so. Voyager 2 followed suit in November 2018, providing crucial data about the heliosphere, the protective bubble of particles and magnetic fields created by the Sun. These crossings revealed some surprising discoveries, including an unexpectedly low temperature in the boundary region, and an unusually strong interstellar magnetic field. The asymmetry of the heliosphere also became apparent, as Voyager 1 and Voyager 2, traveling in different directions, detected differences in the solar wind's interaction with the surrounding interstellar material. In 1990, before its cameras were turned off to conserve power, Voyager 1 captured one of the most iconic images in human history, the pale blue dot. This photograph, taken from a distance of 3.